Hi everyone. For those of you who haven't met me before, I'm Lachlan Gunn. I'm a lecturer at Aalto University in Finland, and I've been working with Shogun and his group on this blinded memory project. So blinded memory is about this idea that if we want to do secure outsourced computation, we have to make sure that untrustworthy software that's running on this machine that we're outsourcing to, we need to make sure that this software can't sort of see or do anything nefarious with the data that we've sent. And the way that we can do this is to impose a kind of hardware-enforced access control. So the idea is that we want to make sure that any sensitive data that is sent to the system, once it has arrived, the hardware won't allow the data to be exported outside the system or to be used in any way that will potentially expose the data. It imposes a kind of access control, if you like, that does taint tracking on the data that's been sent to the system, and this taint tracking is used to decide whether an operation is allowed to occur. So if an operation would copy data straight outside of the system, for example to a network adapter, then it's not going to be allowed. Or if the operation would allow the data to be moved outside of this taint tracking, for example by doing some operation like using it as a pointer that would allow the data to be obtained using side channels, this also is forbidden. So by imposing these kinds of rules, we can make sure that when data has been sent to this remote system, it can't be revealed to anyone except the original client. And so in addition to this taint tracking, we have some specialized hardware that only has a single function, which is to import data and set its taint bit that marks it as sensitive, and then to re-encrypt it and unset its taint bit so that it can be exported back again. So in an earlier lecture we discussed the blinded memory extensions in general, but in this one I'm going to talk about how we did some formal verification of the model to show that the design is secure in the sense that the taint tracking logic that we have, that it really does prevent data from being exported outside of the system. And we did this using the F* language, which is a language used for formal verification that we'll go into shortly. As kind of a bit about my background, I'm originally an engineer, and I've worked on electronics, and I've worked on distributed systems, and I've worked on platform security. I'm not a formal verification person. I use formal verification, but I'm not a specialist by any means. And this is the spirit with which I kind of want to enter into this, to show that even if you're not necessarily a dedicated formal verification enthusiast, you can still use tools like F* to try to prove things that are important to you. In this case, to prove that our model of the blinded memory hardware, that it provides some security properties that we need. So the basic methodology that we had here was that we want to take some function f, which simulates BliMe in some sense, and that shows how the processor will step. Then we express a security property as a predicate on this function, and then prove that this predicate holds for the function f, and then we can do some refinements so that we can show that the security property will hold even as we make f increasingly more complicated. And we did this using the F* language, which is a functional language in the ML family. It's dependently typed. And what this means is that the types of one value can depend on another value. So for example, we can have a function like this one that will take as input one value x, and it can have a return value whose You can have a return value whose type depends on the value of x. So in this case, the return value is always going to be less than the input, and we can say that the return value is always going to be an even number. So this gives us a way to specify properties of a program independently of the implementation. So if we have some function that all we need to depend on is that it has some properties like this, for example, then we can specify that in the prototype, and we can use this to prove properties of the function. But we don't need to see all of the details throughout the proof, and this makes a lot of the verification much easier. And so essentially the type checker will validate the program correctness, because we specified that some values in the function, or in the program, sorry, have a certain property, and the type checker will check, does it have this property? The problem, of course, is that this is quite challenging in practice to specify all of the types properly, but we'll see how this can be made to work. So you can try out some of the things in this talk on your own if you want, following along. So there is a tutorial for the F-star language that you can access here, and it has an interactive editor so that you can type some code into one window, and then you can click the button and it will type check everything. And you can, for example, fill in code with this and try to put in some evaluation that will type check. So I'm not sure if anyone who's watching this live wants to follow along live. So if you do, then please go to this URL. If you are watching the recording of this, then this would be a good time to pause and have a go at filling in this function implementation yourself. Let's continue then. So would anyone like to suggest, well, what would be something that you could put into this function? And you don't have to have necessarily gone to this web page and proven it, but what what would be some example of a function that would satisfy this? So it takes in a value that is equal to 1 modulo 256, and it returns an even value less than the input. So as an example, we could subtract 1 and then divide by 128. And this is always going to be possible because so if x mod 256 is equal to 1, then it has to be greater than 0. So we know that we can subtract 1 and still get a natural number, and we know that the value is going to be smaller because we've divided it by 128. And the type checker will work this out if you try to fill in the details. So we've got another example here of something that you can do. So we might have a function where we can write it in a couple of different ways. We could have an efficient way that is complicated, and we can have a simple way that is obviously correct, but that's slow to execute. And so to give an example of this here, we have a function that will find the cumulative sum of values up to x. And so we can write this in a recursive way, and I think it should be hopefully easy to convince yourself that this implementation is correct. And we can define a prototype for the cumulative sum function that says that for some natural number, so for an integer greater than or equal to 0, the return value is going to be equal to the reference implementation as applied to that input. So this is great. We could, for example, just use reference cumulative sum as an implementation of this. But if you go to compute this, then unless you can do some clever optimization, then it's going to take order X time to execute. So what we would like is a more efficient implementation. Like for example this one, where cumulative sum is half x plus 1. So the problem is that if you just put this straight into F star, it can't prove that this matches that function prototype on its own. It's kind of more complicated than the prover can work out on its own. So types are checked using an SMT solver, which for intuitive purposes you can treat as a magic box that takes in some facts and then outputs yes, no, maybe. And for the type checking to succeed, we need to get yes on all of the different type statements. In this case, the solver wasn't able to prove this. So it got basically a maybe. So maybe this matches the function prototype, maybe it doesn't. And because of this, we need to provide some more details that will let the prover see that, okay, this really does match the reference implementation. And one way to do this is to prove a lemma that says what we want, and then we can invoke that when we implement it. So as an example, we can have this lemma here, which I've just called helpful lemma, which says that for any x, it validates that x times x plus 1 all over 2 is equal to this reference implementation. And then when we go to implement cumulative sum, we can invoke this lemma. This provides this fact here to the SMT solver, and the SMT solver, given the return value and this helpful lemma as inputs, can work out that, okay, cumulative sum matches the function prototype. So the question then is, well, how do we prove it? Here I've just got an admit statement, which just tells the prover, just assume that this is true and we'll come back to it later. So if we want a real proof that this implementation is correct, then we need to get rid of this admit and replace it with something else. If we take it away, then we're going back where we started. This theorem is a little bit too much for the prover to work out on its own. So to start with, we can look at, well, how would we prove this by hand? So we start out with some natural number n, and we want to compute 0 plus 1 plus all the way up to n, and show that this is equal to n times n plus 1 all over 2. There are a few different ways that we could do this. Maybe the easiest one is using a geometric argument where you show that this sum looks like a triangle, and then you can compute the areas and say that, okay, this is n on the one axis and n plus 1 on the other, and this is a triangle, so it's half the size of the rectangle. But this is a little bit hand-wavy for machine-checked proofs, and so the better way to do this is to try to prove it using induction. So if n is equal to 0, then this is really trivial. 0 equals 0 times 1 all over 2. This is just a nice arithmetic statement which both we and the prover can see holds very easily. But then we add this inductive step and we say that, well, if the theorem holds for n minus 1, then we look at this left-hand side. This is equal to 0 plus 1 plus blah, 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 all the way up to n minus 1. And this is equal to n minus 1 times n on 2, add n on both sides, and we get what we wanted, and our proof is complete. So this is how we would prove something like this by hand. But when we go to prove it in F star, what do we need to tell the prover? So F star is really good at reasoning about arithmetic. Arithmetic statements aren't so hard for SMT, but it isn't able to do induction without a bit of help. So what we need to do is spell out this inductive part of the proof. So we take this helpful lemma and we do this if else. So we say if x is equal to 0, then, well, does this hold? Well, yes, it's just this arithmetic statement that reference cumulative sum of x, which the prover can see is equal to 0 just by executing it. That it's equal to that, which again it can compute that, it's equal to 0, problem solved. Then we also look at the other case where, okay, if x is greater than 0, then we invoke helpful lemma. This is recursive, so we can do that. So we invoke it with x minus 1, and we get this fact that we had before, that 0 plus 1 plus all the way up to n minus 1 is equal to x minus 1 times x all over 2. Then it just has to do a little bit of extra arithmetic to work out that, okay, if we add x to this on both sides, then we get what we wanted. And if we put this into the prover, then it verifies correctly. So this is a nice little example of how you can prove some basic functions or basic properties about a function in F star. There are other things in the language which we don't really have time to discuss right now, so you can do things like enums using inductive types. And we use that, for example, to describe a value that might be blinded, where blinded in this case means that it's tainted and not visible to the program. And so we say that a value can be clear or it can be blinded. There are records which are like structs, and there are type classes which let you show some properties about a particular type, and so this lets you do some generic programming. But this was some general information about F star, so let's look at how we applied this to prove properties about BliMe. So the idea is that we model BliMe in F star code, and then we prove the security of this model. So the goal is that changes in this blinded, tainted state, so changes in the data that is marked as sensitive, that these have no effect on data that is not sensitive. So essentially, if any two states only differ in values that are blinded, then after we step the processor, the resulting states should only differ in the blinded values. So the unblinded values the attacker can see, and the blinded values they cannot, and so they can be different. So formally, we model a state transition with a function f, and we define an equivalence relation on the blinded data, or on the state of the system, so that two things are equal if, or two things are equivalent if they are either both blinded or unblinded and equal. And we prove this safety property saying that if input states are equivalent, then after doing a state transition, they will also be equivalent. And we prove this using a refinement approach. So we start with a really generic state transition that looks at a very generic machine. And then we add more and more details. So we add some kind of generic instruction set and then show that if this generic instruction set state transition G is safe, then the machine that results from that is safe, and so we're okay. Then we can add more details and show that, okay, if we build something that looks a bit like a CPU pipeline, that if this is safe, then the instruction set that results from that is safe, and so the machine is safe. And we can do that with then concrete instructions, and we can look at properties of a specific ISA. And combining these all together, we can then show that this concrete instruction set is safe. So as a quick preliminary, we look at how do we represent data. So this blindable state can be either clear or blinded. Later on, there is data that can have a domain tag attached, so you can have blinded data from multiple clients. But for the purposes of this talk, we're going to talk about data that is blinded or not blinded, so tainted or not tainted. And we represent that with this inductive type here that can be either clear or blinded. And you can apply this to any kind of type. So that's what this is about. So you can have a maybe blinded type for any type of data, which lets us then define things like this, where we have we can produce a maybe blinded value that is clear by writing clear x, and then this is a clear value containing x. But we also need to define an equivalence class on maybe blinded. And the definition of equivalence that we have, as I hinted at before, is that two values are equivalent if they are both clear and equal, or they're both blinded. So what we don't allow is two clear values that are different, because you can then just look at the two values and see, is this the same? Or similarly, we don't allow one clear and one blinded, because then we could just try doing some operation and see whether the machine allowed it, and that would tell us whether the value was clear or blinded. But if they're both clear and equal, or they're both blinded, then everything is fine, because we can't distinguish between them in that case. So we start with the most generic possible CPU model, where we just have a state mapping that maps one machine state to another machine state. And this machine state is really generic. It's just some registers and memory and a PC. And so then what we do is we define this this property that if you have equivalent input states to the machine before it's stepped, then after you step them, the system will be in an equivalent state. So this this step exec function here, this is the state transition that we mentioned before, and then this is this safety property that we had that if the inputs are equivalent, then we step the system, the outputs are equivalent, and then we can define this safety predicate on the on this generic description of the machine in terms of this holding true for all possible input states. So that's the most generic model, and the goal is just to verify that this state transition defined by exec here, that this is safe. But now we want to take things a bit further. So we introduce the notion of an instruction. So in this case we have what we've called an execution unit, perhaps slightly confusingly, and then this takes an instruction and input state, an input value, and then maps it to some new output value. So there's a different mapping for each instruction, where the instruction is loaded from memory at the address in PC. So what the model does then is it will fetch an instruction and then do a mutation of the machine state according to the instruction. And this is what it looks like in the code. You don't necessarily have to follow along with the code, because we haven't spent a huge amount of time on F* at this point, but if you're interested, you can just see vaguely how it looks. We load a value from memory at this address PC, and then if the value is blinded, we fault, because we can't have an instruction that depends on sensitive data. But if it's not blinded, then we just execute the instruction based on the current state of the system. And what we've been able to prove is that this state transition is safe, as in the last slide, if this execution unit is safe for every instruction. So before we talked about a generic state transition. So now we say that, okay, we have a different state transition for each instruction. Well, if we look at each instruction individually, if each instruction is safe, then the whole machine is safe. Maybe that's a bit obvious sounding, but it nevertheless has to be proven. So then we start to look at something that looks more like a normal CPU pipeline. So we fetch an instruction from memory, we then decode it to get a set of operands and an opcode. We read the input operands from the state of the machine, be it from registers or an immediate. We then compute the output values that the instruction is going to produce and then write somewhere. And then we write these output values to the machine state. So the parameters to this model are going to be an instruction decoder, which is able to take this instruction word from memory and then map it to an opcode and a list of input and output operands, and what we call here the instruction semantics, which takes this decoded instruction and the input values and then produce an output value and possibly indicate a fault. And we were able to verify that if these instruction semantics are safe, in the sense that we'll see in the next slide, then the resulting execution unit is safe, and then this means that the machine is safe. So what does it mean for instruction semantics to be safe? Well, what we say is that if the inputs from the register file are equivalent, then the result is equivalent. So it's kind of like we had before, but rather than looking at the whole state of the machine, we just have to look at the few operands that we've read from the register file. So for the result to be equivalent, what we need is the fault status to be identical. So we can't have that a sensitive value 0 produces a fault and a sensitive value 1 produces no fault, because then we could distinguish between those two quite easily. So they have to produce the same fault status, and if there's no fault, which means that then there are going to be changes to the machine state as a result of the instruction, then the values that get written to the register file need to be equivalent. So there can't be any different values being written in the clear to the register file as a result of different blinded values. And memory operations have to be indistinguishable in the sense that they have the same addresses, because if you have a memory operation with an address that depends on a sensitive value, then you can get some information about this sensitive value using cache timing side channels. So the memory operations need to have the same addresses, and then they need to have the same source and destination registers, for reasons that I hope are fairly obvious. And you can see down here below what this looks like in code. I won't go through it in detail because that might be a bit tedious. But then finally, after all this, we can prove the safety of a concrete instruction set. So before we had these model inputs that had an instruction decoder and the semantics of the instruction, well, we write functions that can parse an instruction word into an opcode into the input and output registers in an immediate, and we write functions that will implement stores, loads, conditional branches, add, subtract, multiply, and XOR. So it's just a basic model ISA. It's not full RISC-V ISA, but it's enough that you can do general computation, and we can use this to show that when we apply BliMe to a real-ish ISA, then it will still provide security. So there's too much code for me to show it here in the presentation, but I think the highlight here is that we can do things that you call special cases. So it's not just taint tracking in the sense of if an input to the instruction is sensitive, then all of the outputs need to be sensitive. There are some cases where it's not necessarily the case. For example, if we have a sensitive value as an input and then AND it with 0, the result is always going to be 0. So that result is not sensitive. And so we can say that x and 0 is always going to be a clear value 0, even if X was blinded. And we can prove that these instruction semantics are safe, even though we have these exceptions to what a normal taint tracking policy would look like. So this is where we got up to. There are some possible next steps to take this a bit further. So we have a model of what an instruction set would look like in F star, but it would be nice to be able to extract an executable simulation out of this. You can take F star code and then extract it into C or OCaml code. We haven't done that with this, but that would be a sensible thing to do, so that we can take this model and actually run it and use this to make sure that the code that we are running on real processors, that it behaves in the same way as in our model, which would then let us be a bit more certain about how the real ISA works. Then there are some more technical things, so having unblindable registers in memory. So at the moment we say that registers in memory can be marked as clear or blinded, but in practice this isn't necessarily the case, because in a real processor you have memory mapped I/O, and in these cases you don't want to allow data to be extracted via this MMIO. So you want to have faults when you access some instructions or some memory addresses using blinded values. At the moment we have a special case for the program counter, but we could extend this to other regions of memory too. And then the final thing would be to look at more general microarchitectural side channels. So at the moment we show that cache timing side channels can't be used to extract the sensitive data, but real processors do transient execution, and though we are confident that by enforcing these taint tracking rules during transient execution and during speculation, that this will provide security against things like Spectre, it would be nice to have a formal proof of that. So, in summary, F star is a useful modeling tool. It's not difficult to start using, even as a non-specialist, and you can prove lots of interesting things. We were able to show that BliMe's taint propagation rule doesn't leak any sensitive information, and that the model ISA that we've designed, that this implements the taint propagation rule correctly in a way that doesn't leak information, including when we have special cases like X and 0, which make the rule that we implement a little bit weaker than the general one, but that we can still implement securely. But because this is a special case, we would like to show that these special cases don't compromise security, and by implementing this into our F star model we can assure ourselves that these special cases are indeed safe.